7번째 발표에서는 QRT의 사킵 박사님께서 펜토초스 펄스 레이저 시스템을 이용한 반도체 소자의 방사선 영향 특성화 및 허용 오차 테스트에 대해서 발표하겠습니다. 사킵 박사는 파키스탄 컴사츠 대학교에서 컴퓨터공학 학사, 미드 스웨덴 대학교에서 전기공학 석사, 한양대학교에서 전기통신공학 박사학위를 취득하였습니다. 그는 2019년에 반도체 소자의 방사선 효과 특성화 및 몬테카를로 시뮬레이션 전문으로 하는 선임 방사선 효과 엔지니어로 QRT에 입사했습니다. 그는 지상 및 우주 어플리케이션을 위한 다양한 디바이스에 대한 싱글 이벤트 이펙트 그리고 토탈 아이오나이징 도즈 테스트를 수행해왔으며 현재 첨단 반도체 디바이스를 위한 펜토초 펄스 레이저 기반 싱글 이벤트 이펙트 평가 방법을 연구하고 있습니다. 이번 발표에서 사킵 박사님은 레이저 기술을 활용한 방사선 테스트의 범위와 최신 반도체 소자의 방사선 경도를 평가하는 데 적용하는 방법에 대해 논의할 예정입니다. 또한 펄스 레이저 테스트와 관련된 도전 과제를 강조할 것이며 이 강연에서는 펜토초 레이저를 사용하는 다양한 유형의 메모리, 전력 및 아날로그 장치에 대한 수많은 응용 사례가 소개됩니다.
Hello everyone, thank you for joining. Today in this talk, I will be discussing about a very powerful technique to characterize and investigate the radiation effect on microelectronics devices. So it is known as femtosecond pulse laser based single event effect testing. So let's get started. So in the beginning, I would be discussing about the radiation sources, the natural radiation sources, and then how the radiation effect in electronics devices, how the charge is deposited by the radiation inside the semiconductor devices. Then the single event effect testing, which is the conventional method of testing the electronic devices. And then the pulse laser based testing, which is the main topic of this talk. And at the end, I will be giving case studies, few application examples of pulse laser based testing. So basically there are two types of radiation environment. The first one is the space radiation environment, which is the most hostile radiation environment. There are three sources of radiation in space environment. The first one is the galactic cosmic rays, which actually consist of heavy ions and high energy protons. Heavy ions have very, very high energy, up to 1 gigaelectron volt, and they comes outside of our solar system, and they can interact with the semiconductor devices and can have various types of effect. It is isotropic, which means they come from all the direction. The second source is the solar particle. The sun is the most hostile or intense source of radiation in our solar system. It emits high energy proton as well as heavy ions directed towards the earth, and which can penetrate into our earth environment as well. The third source is the Van-Allen belt, the radiation belt which surround our earth. So they form like a donut shape around our earth. They are formed due to the magnetic field of our earth. They provide natural protection to us from this hostile radiation environment. The particles coming from the sun as well as from the galactic origin, they are either deflected or trapped inside these belts and provide us the protection to our electronic system working at the terrestrial heights as well as at the ground level. So the next figure shows how our earth is exposed to the continuous radiation from the sun as well as the radiation from the galactic origin, galactic cosmic rays. You can see that our earth is surrounded by the radiation belts, and it traps the particle from the sun as well as from the galactic cosmic rays. The radiation belts consist of proton as well as electron and heavy ions. The inner belt mostly contains electrons. The outer belt contains the electrons. The galactic radiation comes from the outside of our solar system, and as you can see, the sun is continuously emitting the radiation in form of solar wind as well as the solar flares. The solar flares size could be 100 to 1,000 times of the Earth's size, so they have a huge impact on the electronics working on our Earth and terrestrial heights. Radiation belts, the inner belt is fairly stable, but the outer belt it shrinks and swells over the time, and it depends upon the activity of the sun. Sun has a 11-year solar cycle through which its activities goes to maximum and then comes to the minimum. So the radiation on the Earth depends upon the solar activity. This figure on the left-hand side shows how the magnetic fields surround our Earth. You can see it is thicker at the equator, and it is thinner at the low and high latitude, and it disappears near the north and south pole. So the radiation coming from our solar system, mainly proton, can penetrate into our environment through these poles, and it can undergo nuclear reaction with the air molecule found in our atmosphere, and undergoes a cascade of nuclear reactions to produce a shower of secondary particles. These secondary particles are neutron. They are charged particles like proton, pions, and muons. The charged particles can attenuate very quickly, and they also have very short life, but the neutron, being neutral, can penetrate all the way down to the ground level and can cause disruption in the normal operation of the device. But in this talk, we will not discussing about the radiation in the terrestrial environment. We will be focusing only on the space environment. Next, I will show how the radiation can interact with the semiconductor devices. So here, you can see if a charged particle passes through a semiconductor device, it can lose its energy by generating electron hole pairs by stripping the electrons off from the target atoms to create the electron hole pairs. So this is a plasma of electron hole pairs. So if this pass through or near the junction, p-n junction, the electron could be drifted towards the positive side and the holes can be attracted toward the negative sides. Whenever there's a movement of the electron, we know that the current flows. So energy is transferred to the target material through electronic ionization. The charge is deposited by creating the free electron hole pairs. Some of the electron hole pairs recombine, but majority of the electron hole pairs are actually drifted or diffused to the terminal to cause a current spike. Here you can see the current spike is generated as a result of the current, the carrier drifted towards the bias terminal. This pulse has two parts. The first part shows the current collection due to the drift of the carriers, and the second half shows the current collection due to the diffusion of the carriers. The radiation effect into microelectronics devices can be broadly classified into two categories. The first category is the instantaneous effect, and the second category is the cumulative effect. The difference between these two categories is that the instantaneous effect are due to the single particle strike. They appear instantaneously. There's no way you can predict that the error is going to be generated to be occurred. But in case of cumulative effect, we can see and we can monitor the device behavior, its characteristics to monitor that the device is actually its performance is degrading due to the radiation effects. The cumulative effect of further classified into total ionizing dose, TID effects, as well as the displacement damage effect. In this talk, we will not be covering these effects, so we will only be discussing about the instantaneous effect. So instantaneous effects are basically the single event effects, which are due to the strike of the single particle. Single event effect can further be classified into two categories. The first category is the soft errors, and the second category is the hard errors. As the name implies, the soft errors are non-destructive errors. They are the reversible errors. They do not damage the device permanently. They just only corrupt the data stored inside the device. Once the correct state of the data is rewritten, the device operation is restored. On the other hand, the hard errors are basically the permanent errors or the destructive errors. There is no way to recover the operation or functionality of the device because it is destroyed and the component needs to be replaced. In case of soft errors, there are a number of errors which comes under this category. Single event transient, single event function interrupt, single bit offset, multi-bit offset, multi-cell offset. These are collectively known as single event offset. In case of hard errors, they mostly take place they occur or manifest themselves in the power devices, like power MOSFET, power diodes, as well as the IGBTs. Single event latch-up could also be hard errors, classified as hard errors, because it is the high current state. If it is not prevented in time, it could cause the device to fail due to the very large amount of current flow, which could lead a device into thermal state, and device could burn, and its interconnection could burn, contacts could also burn. So this could also lead to hard error. This table here summarizes all these type of single event effect. Among these, the most common are single event effect, which actually takes place or manifest themselves into memories and latches, which are related to the corruption of information. If a data stored inside the memory and latches get flipped, 0 becomes 1 and 1 becomes 0. MBUs and MCUs are more than one error triggered by a single particle strike. Single event transient can occur in analog devices as well as the mixed signal devices. Single event latch-up normally is a high current state which occur in CMOS devices as well as bi-CMOS devices. Single event burnout and single event gate rupture that manifest into power devices like power MOSFET as well as the BJTs. Now let's discuss why we need to perform the single event effect testing. Testing plays a very vital role in understanding the origin of the single event effect, in validating the effectiveness of the mitigation approaches, to evaluate the sensitivity of the device, as well as, most importantly, to calculate the expected failure rate of the device in the given environment. Accelerated testing is performed, single event effect testing is performed at particle accelerators, where the devices are exposed to the broad beam of heavy ions, which basically simulate the space radiation environment. The primary goal of the single event effect testing using particle accelerators is to find the single event effect cross-section of the device as a function of LT in order to predict their failure rate in the space. Because of the random nature of the individual strike of the particle in the device, broad beams tests do not provide the temporal and the spatial information of the device, which are key to understand the mechanism behind the single event effect. So this is one of the downside of single event effect testing using particle accelerator. Beside this, there are a few other disadvantages, like the very poor availability there are very limited number of particle accelerators available in the world. So to get the beam time for testing and the devices is very hard. It is very expensive, thousands of dollars per hour. So you get very limited time to test your devices. It's not possible to test the devices under all the conditions possible to the exhaustive testing. And lastly, the high turnaround time. This is one of the big limitation and drawback of particle testing. You may have to plan 1 year in advance. Even after 1 year of planning, I mean, it may take a very long time before you can go to the particle accelerator and perform your testing. This figure shows a typical radiation effect facility of heavy ion. We performed testing at this facility last year. It is situated in Finland. This is the radiation room, radiation beam room. You can see the beam is actually delivered from this side. Here we have the vacuum chamber where the DUT can be placed inside this vacuum chamber and exposed to the heavy ion. On this side, you can see this is the control barrack or control room from where the device, you can set the test conditions from here remotely. You can monitor the progress of your test remotely from this room. It also provides the protection from the radiation. This shows how it can be monitored in real time and how the beam is controlled, and as well as the DUT test conditions and the response is monitored through these PCs remotely. This figure shows the vacuum chamber. The testing has to be performed in this vacuum to simulate the space radiation environment. The DUT is mounted in this vacuum chamber, as you can see, and this DUT is connected through these feed-through for different signal cable for the signals and the power interconnections. This DUT is connected through this feed-through. Once this DUT is mounted, the vacuum chamber can be closed and it can be pumped out to perform the heavy ion testing. On the other hand side, pulse laser testing, which is basically not an alternative technique, but is a complementary technique which is used to simulate heavy ions to perform the single event effect testing. In pulse laser testing, the electron, the photon are used to ionize the electron of the target material by injecting the photons at a very specific location, and they can transfer their energy to liberate the electron and they can move the electron from the valence band into conduction band. This is a very powerful tool for injecting the charge in a localized manner into semiconductor devices and structure. So the primary role of this testing is to identify the mechanism responsible for single event effect by injecting charge into very specific nodes and then observing the state and response of those devices. Although the mechanism for producing the electron-hole pairs in matter is different for photons, then the particle accelerator, photon actually free the electrons through the absorption process, whereas the particle transfer the energy to the electron through the Coulomb interaction, but the effect is similar. Laser have been shown to produce the single event effect, which are largely indistinguishable from those produced by the heavy ions. They provide very vital information to develop and optimize the radiation hardened design and to interrogate the spatial and temporal aspect of the device. When we perform the pulse laser single event effect testing, there are a few parameters which are very critical. We have to set those parameters to perform testing. The first one is the wavelength, which determines the absorption in silicon. The longer the wavelength, the deeper it can travel. But longer wavelength have lower resolution as well as they have lower energy. Pulse duration is very critical. Ideally, the short pulses are better representation, and they provide better correlation with the heavy ion testing. Especially for the TPA, we are required to use femtosecond based laser, which means the width of the pulse is in the scale of a few hundred femtosecond. Pulse energy is also very important. It is the sum of all the energy of photons in a pulse. And in single event effect testing, it is in the range of picojoule to nanojoule. Spot size actually determines the beam diameter, and the minimum the better, and but it is limited by the diffraction limit of the light and the optic system. Here I have shown how the photoelectric current is produced. Through absorption, the light is observed to lift the electron from the valence band into conduction band. Photoelectric is a process when the light is shined on the material. The material actually absorb those light, and a photoelectron current is produced if the energy of each photon is greater than the band gap energy of the electron. So here you can see as light is illuminated on the sample, it produces photoelectrons, which means the current is generated or charge is deposited. On the right hand side, I have shown how laser-induced current is produced in a PN junction. Light is illuminated on the sample, which actually photons are absorbed. As a result, electron-hole pairs are generated, and current is collected by the drift and diffusion, and this charge can cause different types of effect. The silicon has the band gap energy of 1.2 electron volt, which means the photon must carry energy above this in order to be absorbed. If a photon carry energy less than this much, it will not be absorbed. It will just pass through the target material, and it will be just transmitted. No energy would be transferred to the target material, which means no charge would be generated. There are two types of techniques used in single event effect test, pulse laser based single event effect testing. The first one is single photon absorption. I will not go into the mathematics and physics behind this mechanism, this phenomena. Single photon absorption is a phenomena in which single photon carries energy more than the band gap energy of the silicon, so it is able to excite an electron from its valence band into conduction band. Charge generation increases linearly with the laser power, and the propagation of charge takes place only in two directions. Carrier density decreases exponentially with distance from the surface. Its density is maximum at the surface, and as we go deeper and deeper, it attenuates exponentially. It can be used for front side as well as for back side irradiation, but it is limited by the penetration depth. The other technique is the two-photon absorption. In two-photon absorption, each photon carries energy smaller than the band gap energy, so individually they cannot create electron-hole pair. But when they combine, two photon combines, they can collectively have an effect to produce one electron-hole pair. To have simultaneously absorption of two photons, then must be packed in space as well as in time. This means we must use a femtosecond laser with very short pulses and use an objective with very high numerical aperture. For the TPA to be dominant, the photon energy should be less than the band gap energy of the material. And the benefit of the TPA, or the main feature of the TPA, is that it lacks the exponential attenuation of the optical pulse energy, which means that there is no exponential attenuation of the energy, and the charge can be deposited at any depth inside the device. The charge generation is only where the focus is. There's no charge generation out of the focus. This figure shows how the SPA takes place. You can see only one photon is required to lift the electron from the valence electron into the conduction band, since the energy is above the band gap of the target material. For the TPA, however, we need two electrons at the same time to be absorbed in order to lift the electron from the valence band into the conduction band. This figure shows the spectrum of the wavelength that can be used for SPA as well as the TPA. Here is the silicon band gap energy edge, which means that the energy above, this is the minimum energy which is required to be absorbed by the target in order to lift the electron from the valence into conduction band by single photon. We normally used these wavelength 1060 nanometer or 800 nanometer or 600 nanometer. If the testing is to be performed using TPA, the wavelength above 1200 are typically used. The typical value is 1260 nanometer, which is used in case of TPA testing, which carries energies less than the band gap energy of the silicon. The carrier distribution you can see for the SPA and for the TPA. In case of SPA, you can see the exponential attenuation of the energy inside the target material. For 800 nanometer, the maximum energy in charge density is at the surface and it is decreasing. But in case of TPA, you can see there's no attenuation at the surface. The charge is only generated at a localized position deep inside the target material. There is no charge generation outside this focus area. The test system used for pulse laser testing looks like this. This is the picture of the system that we have at QRT. So the main component of this system is basically the laser source system, which emits laser pulses at a primary wavelength. The second main component is the OPA, which actually expand the wavelength to a range of wavelength that could be used to perform the testing. This is the optical table. As you know that this pulse laser based testing is largely, very sensitive to the vibration. Any vibration could lead to the could affect where the charge is deposited. It can cause the focus to change, and location of the charge where it is deposited could change. So it's placed on the optical table. This box contains optics inside. It contains various filters as well as energy attenuators in order to have the suitable energy for testing of electronic component. This shows how the inside of this enclosure looks like. The top side actually contains how the beam is routed. There are different lenses, and there's IR camera, then the visual camera, how the beam is routed, and then it is directed to the DUT, which is placed here on the motion stage. There are different objective lenses of different numerical aperture. The DUT can be illuminated using different objectives, and this is the motion stage, which has very, very high resolution, which is helpful for scanning a device at very high resolution. It can move in all three directions. This figure shows the DUT image of the sample using the visual camera. In some cases, if the circuit is beneath the substrate, it cannot be viewed using the visual camera. So IR camera can be used to visualize the pattern through wafer. And here, how the scanning can be performed. This is the die size. Die looks like this, and particular area can be selected on a die for scanning, and scanning could be performed in different patterns. This is raster scanning, and as well as this is spiral scanning, which has a very, very high resolution, very fine resolution. Scanning can be performed using this system. Application of the laser testing. I have listed few applications of pulse laser testing here. It can be used for sensitive node identification in a circuit. We don't know which node of the circuit is sensitive. We can scan the DUT and identify those sensitive regions using pulse laser testing. The DUT can be mapped, scanned, and the SU mapping can be performed for sensitive areas. Latch-up screening can be performed. Single event characterization can be performed. Hardening and mitigation, validation and verification could be performed. Functional reverse engineering can be performed, as well as we can use it to reproduce rare events like SEFI, which might not be manifested during the heavy ion testing at particle accelerators because of their low probability, but they can be reproduced as well as localized using pulse laser based testing. This is the example which shows the pulse laser testing. This is a very simple example of the SRAM device, very old one. This is typical 60 SRAM cell. This is the layout of cell, and different nodes of this single cell are marked here. Scanning could be automized. We can define the grid. We can choose the laser energy for which the device to be tested. You can select the position, strike the laser, and observe the circuit response and reinitialize if there's an error, and then we can repeat it as long as we want it. This is how the scanning of the DUT looks like. So DUT is scanned like this. This is raster scanning for single energy level or first energy level. Then in second step, the energy can be increased and the scanning can be performed. In the third level, energy can be further increased and scanning could be performed, and in this way the mapping could be performed and the threshold could be defined for each node of the device, and the sensitive area can be identified. The second example shows that how increase in energy can find the different sensitive area and the size of the sensitive areas, which can be used to find the cross-section as a function of the laser energy. On the x-axis, we have laser energy, and then y-axis, we have the cross-section. And you can see we can find the cross-section curve as a function of laser energy. Typically, it is plotted as a function of LET in case of heavy ion testing. So it can be correlated with heavy ion testing after the pulse laser testing. This example shows how single event effect laser mapping can be performed for high density memory devices. This is basically a high density DRAM device. The DUT looks like this. You can see different banks on the die. This is the area which is actually the logic area in between the memory area, and more specifically, these are the voltage buffers. This could be selected to be scanned at different energies, and you can see how increase in energy can result in different number of errors. This shows how the number of errors increases with the increase in energy. And similarly, different areas, logic areas inside the memory, or as well as the memory areas, can be selected to identify the areas to different failure mechanism. Like this area is sensitive to latch-up, this is sensitive to SEFI, and this is sensitive to latch-up MBUs, and this yellow region corresponds to the SEUs. This figure shows more detailed mapping. This central region corresponds to the peri region, you can see, and this area corresponds to the memory region on the die. And this scanning was performed as a fixed energy, and each color corresponds to the different type of event observed during the scanning. And this testing was also performed at heavy ion testing, but using heavy ion testing, it cannot be localized which area is producing which type of event, like which area is sensitive to latch-up and which area is sensitive to hard SEFIs and soft SEFIs. But using laser testing, this area could be very mapped very precisely, and the sensitive region for each type of event could be mapped very, very precisely. This is another example for the DRAM devices. We tested this device at QRT. This is very high density DDR4 DRAM, and we reproduced some of the events like Cepheid and latch up. Central region is selected for scanning. This is the logic area. This is the memory area. For this smaller region is selected for the scanning, and you can see this area is basically the peri region, and the lower area correspond to the memory region. So we perform the scanning on each of these areas to reproduce some of the events, and as well as to identify the sensitive locations. And we're able to reproduce Cepheids. This is the result of Cepheid event. Cepheid is an event in which a single particle, a single pulse can cause the thousands and thousands of error and bit locations to flip. And this is the signature of the latch-up event which occurred during the scan testing. This is a single event transient we performed at the QRT. And this is the cross-section of the device. This is basically an analog device, analog comparator. We performed the testing at 1060 nanometer at the pulse width of 200 femtosecond, and at these energies, at 100 megahertz, 100 hertz frequency, there are two devices on a single die. The lower device was scanned at these different energies, and the single event transient of different size and magnitude and shapes were reproduced. This is a very good example. This device is basically was used in one of the NASA's mission. At the very last hour, this device was found to be sensitive to the latch-up. So there was no way that mission could be delayed. So quick screening was performed using laser, and the area which was sensitive to the latch-up were identified. The device was modified, the design was modified and tested again, and it was found immune to the latch-up. This is the example of testing power devices. This is basically a wide band gap device, a GaN device which is built on the silicon. This testing is performed using TPA from the backside. You know that the band gap energy of the GaN material is 3.42 electron volt. So this means that we cannot test this device using using SPA, especially at at the wavelength that we typically use, around 1 micrometer. But what was done in this case was that the testing was done using TPA at this wavelength, 1030 nanometer from the backside, and you can see how the charge was generated from the backside of this device, deep inside the device, close to the sensitive volume or close to the active layers, and the different single event transient were reproduced of different shapes and different magnitude. And you can see this figure shows the destructive event, which is basically the single event burnout was triggered using TPA from the backside. This is another example of the power device characterization. The testing was performed from the front side, and the sensitive area was located along the gate finger. This region was identified to be the sensitive region. There was no other region was identified. HEXFET was not detected as a sensitive area. So the backside testing was also performed. Here you can see the laser is focused from the backside at the depth of around 350 micrometer. The beam was focused at this depth, and the charges was injected at this depth. And this figure shows the damage site before the testing and after the testing, and you can see that the damage site of the single event burnout after the backside testing. And you can also here you can see that the threshold energy as a function of laser focusing depth. Here you can see when the depth is close to 300, 350, the threshold energy is minimum because the charge is injected very, very close to the sensitive volume. As we move away from the sensitive volume, the threshold increases. Pulse laser-based testing also has some limitations besides some advantages. So let's go through some of the advantages. The first one is fast and cost-effective. You can perform the testing in-house if you have your own system. You don't have to go overseas to perform the testing. You can perform the testing right away or at very high speed. The accessibility is very, very good. The spatial and temporal information it provides is very useful. No vacuum is required for the vacuum for the testing as it is required for the heavy ion testing. It is suitable for commercial devices screening. It is compatible with the backside approach as well as the front side approach. I mean, modern devices, it is very hard to test those devices from the front side because of the metal layer, large number of layers, over layers. It is a non-destructive method. In case of heavy ion testing, a particle accelerator, the device may get damaged due to the cumulative effect. But for the pulse laser testing, there's no cumulative effect, so single device is enough for the characterization. As I said, it is high speed and high time resolution. The pulse laser can pass through the insulating layers, but it cannot pass through the metal, which is one of the biggest drawback. Its inability to penetrate through the metal. There's no absolute measure of the threshold for any event, no direct measure of the saturation cross-section, and the cross-section has to be correlated with the heavy ion data in order to find the absolute saturation cross-section, absolute threshold value for the tested devices. This table summarizes the type of analysis which could be performed using each type of methodology. Heavy ion testing can be used, or TPA testing could be used. So there are certain cases in which heavy ion is the best technique, and there are other cases when the TPA laser has benefit over the heavy ion testing. Let's say, for example, for performing the screening of the devices and a different design, heavy ion testing is not suitable because it requires lots of time, which involves the cost. TPA, SPA can be used very effectively, but in order to find the SEU cross-section as a function of LET, TPA or SPA laser cannot be used. Only heavy ion is effectively used in that case. Testing fault-tolerant system or analyzing deep charge collection can be done very effectively using TPA. Mapping of the latch-up areas for the flip chip devices can be done using TPA. Validating latch-up free design could be done effectively using heavy ion. But finding rare events like Cepheid and validating the radiation hardened design, laser is the best technique to perform those type of analysis. So in the summary, the pulse laser testing is basically a complementary tool for the characterization and validation. It is not meant to replace the heavy ion testing. It is always used in conjunction with the standard method to effectively test and characterize a device, single event effect response, and sensitivity. It is very powerful and convenient method to extract information, design information, device information that is otherwise not possible with the particle accelerated standard testing. Using the optical method, it allows to identify the sensitive nodes and reduce the radiation testing time needed to find the upset threshold as well as the saturation cross-section. So before going to a particle accelerator, heavy ion testing could be, before going to heavy ion testing, laser testing could be performed to identify the different test conditions, to identify the threshold and saturation levels, to reduce the time required to test the devices at the particle accelerators. And a TPA, although it is expensive than the SPA, it is preferred because of the its utility or possibility for the backside testing, as well as the 3D mapping of the devices, and it is more close to reproduce the effect of radiation testing than we can do using SPA. So thank you very much. If you have any questions, so don't hesitate to contact me through my email. Thank you once again.